Drop a complex, multi-step enterprise query into a standard retrieval-augmented generation pipeline, and the system usually collapses. Single-agent setups struggle to maintain logic when forced to juggle overlapping databases, ambiguous questions, and dense technical requirements all at once. Bayer's preclinical drug discovery division provides a perfect stress test for this problem. Researchers here need absolute precision to determine the safety and efficacy of new compounds, and a hallucinated or incomplete answer can derail critical scientific timelines. The required data is split across two entirely different formats. Researchers must query highly structured, modern datasets alongside massive payloads of unstructured text, specifically decades of scanned PDF study reports containing nuanced scientific narratives and complex tables. A common assumption is that extending a large language model's context window solves this. If a model can process 1 million tokens at once, you should technically be able to feed it the entire database and ask for an answer. But treating the prompt as one massive container creates context pollution. Injecting too much varied information into a single pass dilutes the model's attention. It struggles to steer logic, loses track of specific formatting constraints, and generates outputs that engineers cannot accurately trace or evaluate. Reaching production-grade reliability requires abandoning the monolithic prompt. We have to architect how information is routed before it ever reaches the model. This discipline is called context engineering. Instead of giving the model everything at once, the system is designed to route strictly filtered, highly specialized context payloads to dedicated agents at specific stages of a workflow. A planning agent receives only the context required to chart a trajectory. A retrieval agent sees only search indices. A writing agent receives only verified events and formatting rules. To orchestrate routing, we rely on a second pillar, harness engineering. We contrast a free-thinking model on the left against a multi-node Landgraph circuit on the right. This scaffolding locks the model into a strict workflow, enforcing tool boundaries, state persistence, and reflection loops. Autonomous agents left to their own devices are highly unpredictable. Deploying them into an enterprise environment requires a rigid framework to bound their autonomy and enforce observability at every decision point. Looking at Bayer's Prince architecture, the first node in the harness is designed to clarify user intent. It acts as a fail-fast mechanism. If a researcher submits a vague query, this node pauses the workflow and asks the user for missing parameters. Locking in domain constraints up front prevents the system from burning compute on expensive trial-and-error searches across the wrong datasets. Once the intent is clear, the query advances to the think and plan node. This node executes process reflection. It has no access to the underlying scientific data. Instead, it evaluates the agent's current workflow trajectory. It pauses to ask, am I selecting the right tools to achieve the user's goal? In a system with dozens of overlapping databases covering pharmacology, toxicology, and metadata, tools often look identical to an LLM. This metacognitive pause allows the agent to explicitly reason about subtle tool boundaries before executing a search. Without this step, agents run blind. They will execute a linear sequence of database calls, assuming forward motion is the same thing as actual progress. Once a plan is set, the think node hands off to the researcher agent. The researcher acts as a coordinator, delegating the query into two highly specialized retrieval pipelines to prevent cross-domain data leakage. In the first pipeline, designed for unstructured PDFs, the query hits a dual extraction process. Language models concurrently pull exact keywords from the prompt while generating precise metadata filters to instantly narrow the search space. A separate model then takes the original prompt and rewrites it into 5 parallel, semantically similar queries to catch phrasing variations in the historical texts. Those 5 queries simultaneously hit the OpenSearch database. The system executes a weighted hybrid search, scoring results heavily on semantic meaning while reserving a 30% weight for exact keyword matches. To finalize the unstructured retrieval, a cross-encoder re-ranker evaluates the aggregated chunks against the original user question, isolating the top 7 pieces of evidence. Meanwhile, queries requiring precise numerical filtering or study metadata are routed to the text-to-SQL pipeline, querying Amazon Athena. Here we see strict context engineering in practice. The system never provides the LLM with the full database schema. Using dynamic few-shot prompting, the system retrieves and injects only the exact tables required, alongside proven semantic examples of correct SQL syntax. This guides the code generation and eliminates the risk of the model hallucinating table relationships. By decoupling retrieval into these distinct, carefully weighted pipelines, the architecture safely bridges the gap between historical narrative documents and strict relational databases. The retrieved data is not sent directly to the user. First, it passes to the reflection agent to execute the second modality of evaluation, data reflection. Process reflection ensures the system takes the right steps. Data reflection ensures those steps actually produced evidence. A perfectly executed search can still yield blank or insufficient results. The reflection agent compares the retrieved context strictly against the user's initial query. If it identifies missing variables, it generates targeted follow-up searches and routes the workflow backward to fill the gaps. Once the data is verified, it moves to the final stage, the writer agent. This node runs draft reflection, enforcing specific tabular formatting, checking for required sections, and applying exact source citations before the output is finalized. Beneath all of this moving logic sits the defining feature of the engineering harness, state persistence. Every time a node completes a task, the exact state of the workflow graph is committed to a Postgres checkpointer. If an external LLM API drops mid-task, the entire application does not crash. The system can pause, wait for the user to hit retry, and resume execution precisely at the point of failure, without discarding any prior research. True enterprise resilience relies on this architectural ability to gracefully recover from the inevitable hardware or API fault. Looking at the completed Prince workflow, we can see strict information isolation in practice. Planning context, retrieval context, evidence context, and synthesis context remain completely separate. This isolation enables 3 distinct layers of safety. Process reflection corrects the agent's trajectory. Data reflection validates the retrieved evidence. Draft reflection secures the final synthesis. Future models will naturally absorb more internal reasoning capabilities. However, heavily regulated enterprise environments will always require explicit, observable control over exactly how logic is routed and verified. The path to reliable AI is built by engineering a meticulous harness around the model, one that bounds autonomy, strictly manages context, and demands verifiable proof at every single step.